All right, let's talk multiple linear regression. We're moving beyond just a single cause.
Simple regression is great, but in reality, outcomes usually have multiple drivers.
So we just expand the equation, adding more variables, each with its own coefficient.
Okay, we've added all these new predictors, but is the model as a whole even useful?
That's where the F statistic comes in. It tests if all our coefficients are just 0.
And look at this, a huge F statistic and a tiny p-value. That's exactly what we want.
That tiny p-value tells us that, yes, at least one of our predictors actually matters. So, the whole model has value, but which specific variables are pulling their weight?
For that, we do the same thing as in simple regression. We check their individual p-values.
And yep, both LSTAT and age have small p-values. They're both statistically significant here.
We know the model is useful, but how well does it actually fit our data?
We turn to our old friends, R-squared and the residual standard error, to measure quality.
Now, what about a tricky situation when you have more features than actual data points? Well, that's a big problem. The model will overfit. It basically just memorizes the data.
And this gets to a key question. Are you trying to understand relationships or make predictions?
Because if your goal is prediction, the only thing that matters is how it performs on new data.
To check that, we use a fundamental technique, the train-test split. It's a must-know.
The training error can be misleading. The test error, now that's the real report card. But if you're just trying to understand relationships, you might not need that split.
So yeah, multiple regression is powerful, but with that power comes a lot more complexity.
And this is the constant balancing act, adding power without just memorizing the noise.